Good morning. The next topic in our syllabus is advanced counting techniques. Advanced counting techniques. So already we have covered counting techniques, which is permutations and combinations. In this topic, we will try to cover recurrence relation, solving recurrence relations, and generating functions along with it. So what do you mean by recurrence relation? What is a recurrence relation? So a recurrence relation is basically for a sequence. Suppose we have a sequence an. If there is a sequence an and it is an equation that expresses equation that expresses an in terms of in terms of one or more of the previous terms of the sequence, one or more of the previous terms of the sequence. Suppose we have a0, a1, a2 and so on up to an minus 1 for all integers n with n greater than or equal to n0, where n0 is a non-negative integer. A sequence is called a solution of a recurrence relation if its terms, so a sequence is called solution if its term satisfies the recurrence relation. So for example, if we want to take a recurrence relation, Sn is equal to n plus Sn minus 1. This is a recurrence relation where Sn is the sum of the first n positive integers. So if you remember, if you want to find the sum of n integers, if you begin with S0, then or S0 will be 0 plus, or you have to begin with S1. So S1 will be 1 plus S0. S0 is simply 0. So S1 is 1. After that, S2 will be 2 plus S1. S1 was 1, so 2 plus 1. S2 is 3. 1 plus 2, which is 3. So this is your recurrence relation. What are we doing over here? Sn is the sum of the previous sum n minus 1 plus the current number. Okay. Similarly, if we have the geometric progression, it is also a recurrence relation. That is, if we have a number Pn is equal to r into Pn minus 1. It is a recurrence relation where Pn is the nth term of the geometric progression with common ratio r. Okay, suppose if I am taking P1 is equal to my r value is 2 and 2 into P0, P0 value is simply 1. So P1 will be 2. Again, after that, P2 will be R into P1. R is 2 and P1 is 2. So this is 2 square. So this is simply the powers of 2. Okay, 2, 2 square, 2 cube and so on. Apart from that, suppose if we have an be a sequence that satisfies the recurrence relation an is equal to an minus 1. So an is the sequence an minus 1 plus minus an minus 2 for n is equal to 2, 3, 4 and so on. And suppose that a0 is 3 and a1 is 5. What are a2 and a3? How do you find a2? a2 will be 2 minus 1 is 1. So a1 minus 2 minus 2 will be 0. So a2 is a1 minus a0. 5 minus 3, which is 2. So a2 is 2. After that, what will be the value of a3? These kind of problems have been already given in your important questions for unit 2. So that is, I have given you some initial values and I have given you an equation. You have to substitute the initial values in the equation accordingly. So a3 will be a2 minus a1. What is the value of a2? a2 is given as 2 while a1 is 5. 2 minus 5, so this is minus 3. Okay. So these are the few examples along with the introduction of your recurrence relation. So we are beginning with this topic. Now let's move on to the next. Let's see a formal definition first. Now, before seeing the formal definition, I'd like to give you an example of why do we need recurrence relation. Suppose we have a factory where the number of pens, there are pens being produced in a factory, the number of pens is doubled every hour. So as the machine gets better, the number of pens is doubled every hour. And if the at the beginning of the manufacturing, we begin with 5 pens, okay, and how many pens will be present or how many pens will be manufactured in an hour? So the question is, how many pens will be manufactured in an hour? Okay, so now for that, to solve this problem, let's have an be the number of pens at the end of the hour. So in this case, an is the number of pens at the end of the hour. So an is given as, so an is given as, since it is being doubled every hour, I'll be using 2 into the previous hour's value. So 2an minus 1 whenever n is a positive integer. So by this we can get the value at the nth hour, where our initial condition at the beginning, our a naught, is given as 5. Okay. So for these kind of problems, for these kind of counting problems, it is beneficial for us to use recurrence relation. And some of the counting problems which could not be solved, so we cannot use permutations and combinations for these kind of counting problems. For that reason, it is better to use recurrence relations and to solve the problem. Okay, now let's see the definition. So a recurrence relation for the sequence an is an equation expressing an in terms of one or more of the previous terms of the sequence. So this has been discussed already, that a1, a2, a3 and so on up to an minus 1 is the sequence. Then the next term in this series is in some kind of the represented with some of the previous terms. Either it may be the sum, difference or multiplication, but it is being represented in terms of the previous term. A sequence is called a solution of a recurrence relation. So a sequence is called a solution of a recurrence relation if its terms satisfies the recurrence relation. So for example, I had taken the sequence an is equal to 3 into an minus 1. If this is the sequence, then what will, and a1 is given as 2. So a1 is 2, what will be a2? A2 will be 3 into 2, okay, 6. So this sequence 2, 6 and so on, this is a solution of your recurrence relation given over here, okay. So this is a recurrence relation definition. Now apart from that, whenever you have a recurrence relation, we will also have, there is an important connection between recursion and recurrence relation. Okay, a recursive algorithm provides the solution of a problem of size n in terms of the solution of one or more instances. Now let's see, what do you mean by initial condition? The initial condition for a sequence specifies the terms that precede the first term where the recurrence relation takes effect. So that is, suppose if we have a series, then it will specify either a naught, a1. These kind of terms are your initial condition. That is, they specify the first term in your sequence. Okay, and by using these terms, either a naught or a1, depending upon your series, you can find the next term a2, a3, a4 and so on. So the best example for this kind of to explain initial condition is your Fibonacci sequence. Fibonacci sequence. In this in the case of Fibonacci sequence, what was the initial condition? F0 was 0 while F1 was 1. Okay, 0 and 1 are the two initial conditions. Apart from that, what will be the next term of the sequence? The next term of the sequence is the sum of the previous two terms. So over here, the next term will be 1, 0 plus 1. After that, 1 plus 1 gives us 2, 1 plus 2, 3, 2 plus 3, 5, and this continues till infinity. Okay, so this is the meaning of initial condition. Now, the recurrence relation and the initial condition uniquely determine a sequence. What does that mean? Whenever you have recurrence relation and initial condition, both of them together determine a sequence. That is, that sequence will be unique to both of these. If we are considering recurrence relation along with a initial condition, then that determines a sequence. This is the case because the recurrence relation together with initial condition provides a recursive definition for the sequence. Okay, so this is the initial condition. Now, after that, modeling with recurrence relation. So for this, in the case of recurrence relation, we will see a few examples. So the recurrence relations are used to model a variety of problems such as, so a few of the examples of your recurrence relation uses are, so this one is given over here, which is growth of a bank account, or it can also be said as a finding compound interest. Okay, or the next example is counting rabbits on an island. Counting rabbits on an island. Then determining the number of moves in the tower of Hanoi puzzle. So let me just write Hanoi tower. And then finally counting bit strings with certain properties. This is the computer science application. Although it is not studied in detail, but this is an important application of the recurrence relation. Okay, so counting bit strings with certain properties. Now in our case, we will see finding compound interest, and counting rabbit on an island is basically your Fibonacci sequence, which is represented graphically. So this also we'll see in bit, and Hanoi tower is also a very important example. Now let's see this in detail. For this example, let me show you it clearly first rather than directly on the screen. So suppose that a person deposits rupees 10,000. So a person is depositing rupees 10,000 in a bank. And why is he depositing? It is a savings account and it is yielding 11% per year with interest, which is compounded annually. So basically it is a compound interest problem. It is a compound interest problem. So the 10,000 rupees are deposited in a savings account, which yields 11% per year interest. Okay, so this yields 11% per year interest. How much will be in the account after 30 years? So the question is, how much will be in the account after 30 years? So one way to solve the problem is every year add 11% interest and then calculate the value and keep on doing it for 30 times. Okay. So suppose for the solution, let Tn denote the amount after n years. Amount after n years. Okay, and the amount in the account after n years equals the amount, so Pn will be equivalent to basically amount in the account after n minus 1 years plus interest for the nth year. So the sequence Pn satisfies the recurrence relation. It will be as follows. So the recurrence relation will be as follows. Pn minus 1, okay, this is the amount in the previous year, nth year minus the nth year amount with the n minus 1 plus 0.11 into Pn minus 1. Okay, why am I multiplying 0.11? Because it is 11% interest on the total amount which we have got. So this will be basically 1.11 into Pn minus 1. Okay, so the initial condition for our problem is P naught. So at the beginning of the time we have 10,000 rupees. So it is 10,000. So in this case, P1 will be P1 will be 1.11 into P naught. Why is it 1.11 into P naught? The entire amount 10,000 plus the 11% interest on 10,000. Okay, so it will be 1.11 into P naught. What about P2? P2 will be 1.11 into P1. Okay, every time I am using this equation. So P2 will be 1.11 into P1. What is the value of P1? Take it from over here. So it will be 1.11 into 1.11 into P naught, which is simply 1.11 whole square P naught. Okay. Similarly, P3 will be 1.11 into P2, which is given as, again, what is P2? 1.11 into P naught. Alright, so this is 1.11 whole cube into P naught, and this will continue until Pn will be given as 1.11 into Pn minus 1 from over here. After that, this can be written as 1.11. So P3 was 1.11 whole power 3. Pn will be 1.11 whole power n into P naught. Why is it this way? Because each time we were seeing that if we were putting our initial condition in the equation, it was being raised to the power whatever the term is. So if the term is second term, it is being raised to the power of 2. If the third term, that is power of 3. So similarly, if we have nth term, it will be raised to the power of n. Now, why do we need to find this relation? The reason being, suppose if we want to find P30 in our case, so in the case of our problem, we need P30. For that, we will need P29. For P29, we will need P28, and this series continues till we get P0. But if we use this formula, we can directly substitute the value of n over here, and we can raise it to that power. So Pn is given as 1.11 whole power n P0. So if we want to find P30, P30 can be easily found out by P30 is equal to 1.11 whole power 30 into whatever the value of P0 is, which is 10,000. So this is easier to find and we can use it easily. Now instead of P30, if we had P100, after 100 years, we can still find it out by just raising the value 1.11 to 100. Okay, so this is the reason why we need recurrence relations. Now after that, the next problem is finding an explicit formula for Fibonacci series. So for this, I'll just solve the problem first. What is our Fibonacci series? Fibonacci series is given with the initial conditions f0 is equal to 0, f1 is equal to 1, and the relation is given as, the recurrence relation for the Fibonacci series is given as fn is equal to fn minus 1 plus fn minus 2. So for this, we have to find the explicit formula. To find the explicit formula, so we will study the formula in detail in the next topic of this chapter. But for now, I'll just give you the basic steps to find the explicit formula. What do you mean by the explicit formula, and why do we need it? We just found out the explicit formula earlier for the compound interest, where we were raising 1.11 to the nth power. Similarly, over here, instead of one initial condition, we have two initial conditions. So what should we do? The steps to be followed for that are as follows. So the first step is we have to find the characteristic polynomial. We have to find characteristic polynomial. Then after that, factor it, determine the form of an, determine form of an. An is the nth term, an, and then finally solve for the coefficient. Solve for the coefficient. Now, how are we supposed to start this problem? First, we are supposed to write the characteristic polynomial. For the characteristic polynomial solution, let me start it over here. If we have fn is equal to fn minus 1 plus fn minus 2, take the entire n these terms on the other side and make it equal to 0. So fn minus 1 minus fn minus 2 is equal to 0. After that, you have to create a characteristic equation or characteristic polynomial. How do we create that? Whatever term you have, take a variable and raise it to that power. So r, here we have the nth term, so r power n minus 1, so r power n minus 1 minus r power n minus 2 is equal to 0. Now, since we have this last term r power n minus 2, we can divide the entire equation by r power n minus 2. So we get r square minus r minus 1 is equal to 0. Okay, so this is basically the characteristic polynomial, which is the first step, the characteristic equation or the polynomial. So we generally call it as the characteristic equation in the prescribed textbook. So let me just write it. The characteristic equation is r square minus r minus 1 is equal to 0. Now we have to factor it or find the roots of the equation. So the roots of the equation will be, if you remember the formula is minus b plus or minus root of b square minus 4ac by 2a. So by using that formula, I will get the roots as 1 plus root 5 by 2 and 1 minus root 5 by 2. So now based on this, we will study a few formulas, but for now I'll just write it directly. That is, whenever you get two different roots, then your fn or an will be given as alpha 1 plus root 5 by 2 whole power n plus beta 1 minus root 5 by 2 whole power n. Okay, you introduce two temporary variables alpha and beta, or two temporary constants actually. So where alpha and beta are some constants. Alpha comma beta are some constants. Okay. So now f naught is given. We have been, the initial conditions were already given for our problem. What were the initial conditions? Initial condition was f naught is 0, f1 is 1. So for f naught being 0, what will be our equation? Just substitute n value as 0. N value, if it is 0 and f naught is 0, then we will get alpha 1, or sorry, alpha power 0 will give us 1. So alpha plus beta is equal to 0. What about f1? f1 is equal to 1. So it will give us alpha into 1 plus root 5. I am substituting n value as 1. 1 plus root 5 by 2 plus beta into 1 minus root 5 by 2 is equal to 1. Now, after that, we have to solve these two equations. Consider these two equations as equation 1 and equation 2 and solve these two equations. When you solve these two equations, alpha value will be 1 by root 5, beta value is minus 1 by root 5. Now substitute these alpha and beta values in this equation. So fn will be 1 by root 5 into 1 plus root 5 by 2 whole power n, and this will be minus 1 by root 5 minus 1 by root 5 into 1 minus root 5 by 2 whole power n. Okay, so this is the explicit formula that we needed to find. What is the explicit formula? Directly by using this formula, we can find f100 or f200 or any n number that you want. In beside finding, like in the previous case, we used to find the previous terms. Now for by using this formula, we won't need the previous terms. We can directly find here f n value. Okay. Now the next example is the Hanoi Tower. So what do you mean by the Hanoi Tower example? The Hanoi Tower is basically a popular puzzle of the late 19th century called the Tower of Hanoi. Okay, it consists of pegs mounted on a board together with discs of different size. So this is known as a peg, and these are the discs of different size, with the largest disc placed on the bottom and the smallest disc placed on the top. The rule of the puzzle is it allows the disc to be moved. There are two rules. What are the rules? Allow the disc to be moved one at a time. So it is given over here. Only move one disc at a time, and never set a larger disc on a smaller one. That is, if you have a smaller disc on the bottom, you can't place a larger disc on the top. Now, how can we shift these discs and how many moves do we require? What are the number of moves? Okay, so for this problem to be solved, let's see first with only two discs as an example. Okay, so if we have this Tower of Hanoi, the goal is to move all the discs to this peg 3 or post 3. The rule is that a bigger disc cannot be placed on the smaller disc. If we have only two discs, how can we do it? It can be done easily. That is, we move the smaller disc to peg 2. So this is here peg 1, peg 2 and peg 3. We are moving the smaller disc to peg 2. This is being moved to peg 2. Then we are moving the largest one to peg 3, and then finally we can move this one from here to here. So over here it is being moved to this peg. So finally we have moved from peg 1 to peg 3. In how many moves we required in total? 3 moves, a total of 3 steps. Similarly, if we have 3 discs, how many moves will we require? For 3 discs, if you notice, this is the way the problem is solved. Okay, so first we move the smaller disc and then we place it, and it is a little bit difficult if we have 3 discs. Okay, and it requires a total of 7 steps. Now, what is the Hanoi recurrence relation? Let Hn is equal to H1. The initial condition is Hn denote the number of moves. Okay, needed to solve the Tower of Hanoi problem with n is the number of disc. N is the number of disc. Okay, and the initial condition is H1, which is equal to 1, because one disc can be transferred in one move from peg 1 to peg 3 according to the rules of the puzzle. What about 2 discs? We required 3 moves. For 3 discs we required 7 moves. So it can be easily written in this way: 2 into H1 plus 1 in the form of a recurrence relation, 2 into H2 plus 1, and so on. Hn can be written as 2 into Hn minus 1 plus 1. Okay, so if you want to find H4, how many moves it will require? It will require 2 into H3 plus 1. So H3 was 7, 2 into 7 plus 1, which is equivalent to 15. So it will keep on increasing exponentially. Now the approach to solve your recurrence relation is in this way. So over here, iteratively, if we solve the recurrence relation, we know that Hn is given as 2 into Hn minus 1 plus 1. This can be written as 2 into Hn minus 2 plus 1 plus 1. what am I doing basically is I am replacing this hn minus 1 by using the recurrence relation formula, which will be 2hn minus 2 hn minus 2 plus 1. So I am using this formula and replacing it. After that, it can be written as 2 square hn minus 2 plus 2 is multiplied with 1, so 2 plus 1. After that, again replace hn minus 2 with hn minus 3, so it will be 2 into hn minus 3 plus 1 plus 2 plus 1. So this will be 2 cube hn minus 3 plus 2 square plus 2 plus 1. And if we continue doing this, it will result in hn will be equivalent to 2n minus 1 h1 plus 2 per n minus 2 plus 2 per n minus 3 and so on up to 2 plus 1. What is the value of h1? h1 for moving one disk was 1. So this will be 2 power n minus 1 plus 2 power n minus 2 n minus 3 and so on up to 2 power 0 basically. So this can be written as the sum of the powers of 2. It is equivalent to 2 power n minus 1. Okay. So this is the Hanoi-Towers recurrence relation. So if you have H7, it will be 2 power 7 minus 1. H7 will require 2 power 7 minus 1, which is around 127 moves. Okay. So it is increasing exponentially. The Hanoi-Towers, the number of moves, if we increase the disk, it will increase exponentially. And this concludes here recurrence relation modeling examples.